Hello, sorry that I had to be out today, but I'm hoping today's notes will be pretty basic and it's all just a review from Algebra 1 and maybe just a little bit of Algebra 2 for you. So hopefully it shouldn't be too bad. So let's go ahead and start the notes. This section is 1-2, linear and quadratic functions. If you need to stop the video at any time, feel free to pause or rewind if necessary. Okay, so I'm just going to start this notes by essentially just spewing out a bunch of formulas for you. I'm not going to go into examples because I think they're pretty basic and I don't want to waste a lot of time doing that. So let's just start. Slope-intercept. Slope-intercept is one form of a linear equation. This is the most popular form. It is your y equals mx plus b form, where of course your m is your slope and your b is your y-intercept. Another form for your linear equations would be your general form. This isn't the most useful form. I find it the most useful if I plan to solve a system using elimination. Or it can also be useful if you want to find your x and y intercepts, but it's not as useful. This is when your x and y are on the same side of the equation and your constants are on the opposite side. Last but not least, we have our point-slope form. This is actually going to be the most useful form in calculus because we'll be writing a bunch of tangent lines, and we'll be doing this with the point-slope form. This is the form that I particularly like, but there's another form you could use as well. I don't care which one you use as long as it's mathematically correct, but the one that I tend to prefer myself is y minus y1 equals m times x minus x1. You could also, this equation is also seen with the y1 on the opposite side added on the other side. So for the point slope, all you need is your slope, m, and then any point on the equation. This equation is not unique, unlike the slope-intercept, which is unique. So that's why math teachers tend to prefer the slope-intercept since it's unique, one correct answer. But the slope-intercept will still work. The point slope will still work if you're just trying to write an equation. Next, let's talk about the slope. The slope is your change in your y over your change in x, or y2 minus y1 all over x2 minus x1. The most important thing to remember is that you're consistent. If you're starting with the second slope for the y's, you have to start with the second slope for the x's. So just make sure that you are consistent in your difference on the top and the bottom. Now along the same lines, we have possibly a new vocabulary word for you, and that's an increment. Increments are essentially the measure of the change in y or the change in x. So the x increment, or delta x, is just x2 minus x1. Now here, unlike the slope, order does matter. Whatever the second coordinate is, we're going to take that x coordinate minus the first x coordinate. And here, a positive or a negative will tell us something. So if your x increment is positive 5, that means that your x increased by 5 units. Whereas if your increment is negative 5, that means that your x coordinate decreased by 5 units. So order does matter. So pay particular close attention to what is your first point and what is your second point, because you always will subtract the second coordinate minus the first. The y increment is obviously just going to be delta y, y2 minus y1. And again, order matters. You must take the second y coordinate minus the first y coordinate. Special lines, we have a horizontal line, which takes the form of y equals b. Now, something I'm a stickler for. If you are writing the equation of a horizontal line and you just write 5, I'm going to mark it wrong because 5 is not a line. 5 is a value. Y equals 5 is an equation of a line. So if I ever ask you to write a tangent line, or if I'm asking you for the equation of an asymptote or whatever it might be, you need to make sure that you write it in equation form, not just a value. So our horizontal line will be y equals, and then of course our vertical line would be our x equals. So a vertical line will take the form of x equals some value, so like a. Okay. Next fact is about parallel and perpendicular lines. In calculus, we study slopes. So we're mostly concerned about the slopes of parallel and perpendicular lines. Parallel slopes will be the same, whereas perpendicular slopes will be opposite reciprocals. And I forgot to mention, pardon my sloppiness, I'm actually doing this on a tablet, so it's kind of hard to do. Or you may hear this as negative reciprocals as well. This means that the slopes will be opposite signs, but also flipped as well. All right, now the quadratic. So your basic quadratic form takes the place, or I should say looks like, ax squared plus bx plus c. We can do a variety of things with the quadratic form of an equation. If we have not necessarily a function, but just an equation, we can actually solve it in a variety of ways. So let's take a look at 3 ways to solve a quadratic equation. The first way that you should attempt is factoring. So when you have a quadratic, such as this one, you want to first make sure that it's set equal to 0, because you can't factor unless it's set equal to 0. I've seen a lot of people try to do some fancy, or I should say incorrect math, factoring before it's set equal to 0, and they get some crazy answers. So make sure you always have the quadratic equation set equal to 0 first. Next, you want to set up 2 factors and consider the products of both the leading term and the last term. So the leading term is 2x squared, so the possible factors would be obviously 2x and x, and with 3 the factors are 3 and 1. So now the question is, should I put the 3 on the left or the 3 on the right? And how you place it will actually be determined by the middle term, because whatever the products of the outer and the inner are, they need to add up to that middle term 7. So for example, let's just say I put it here, the 3 here, and put the 1 here. So if we try out the 3 with the 2 and the 1 with the x, we look at the inner and the outer factors, 3x and 2x, and if you add those up, you only get 5. So we notice that it doesn't quite add up to 7, so let's try switching our 3 and our 1. So now, multiplying our inner and our outer, we get 7, which is wonderful. That means that these are the correct factors. And something to note, since our last term is positive, that means that they both have to be positive or both negative. So you want to also take that into consideration as well, the signs of the values. Okay, so this is our correct factored form. Now using the zero product property, we'll set each of the factors equal to 0 and solve them individually. So I'm just quickly solving here, and I see my first factor, or my first solution is -1/2, and my second solution is -3. Okay, so that's factoring, probably the easiest of the three. The next method will be the quadratic formula. So I'm just going to show you why you can't factor in this particular one. If I try to set up my factors, 2x and x, and 3, if I try to pair the 3 and 1 like this, I would get 3, 2, that'd be 5, doesn't get me to 6. If I swap them, I get 1, 6. If I add them, that gives me 7. I can't subtract them because, again, they have to both be positive or both be negative. So factoring isn't going to work here. So as soon as I realize that factoring is not possible or possibly too difficult, maybe there's too many choices, then I would probably turn to the quadratic formula to solve this. So the quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac all over 2a. The a, b, and c obviously refer to the coefficients in front of each term. So for this particular problem, we get -6 plus or minus the square root of 6 squared minus 4 times 2 times 3, all over 2 times 2. And then we can quickly simplify here. Underneath the radical, we have 36 minus, 24, and 36 minus 24 will give you, 6 minus 24, that gives me 12, all over 4. And while this is your answer, I want to go ahead and reduce this a little bit further by simplifying the radical. So I could pull out a perfect square 4 as 2 radical 3. And you can simplify this a little bit further by dividing out the 2 to every single term. -3 plus or minus the square root of 3 all over 2. And this is actually our 2 solutions. All right, I want to take a look at one more way to solve for a quadratic, and that's completing the square. And we're actually going to use this to complete the square of an equation to find the vertex. Okay, let's take a look at an example. Here I have the function f of x equals 3x squared minus 12x plus 7. All right, to complete the square, the first thing that you want to do is factor the leading coefficient out of the x squared and x terms. So the leading coefficient is 3, so I'm going to factor that out. I'm going to leave a gap in this set of parentheses with my coefficient out in the far right. So once again, I factored out the a term. And that was from our x squared, from x squared and x terms. Next, you're going to complete the square. To do this, you're going to cut your b term in half, or what your remaining b term is, in half, and then square it. So half of -4 is -2. Squaring that, you get a +4. And then you also want to balance the equation. And to do that, you want to subtract a term on the other side. Now, I don't want to subtract 4 because what I'm actually adding is not 4, I'm adding 12 here with this 3 in front. So I'm actually going to subtract 12 to balance out this equation. So that way I'm actually not changing it. Next, you'll factor the perfect trinomial here. So here we have x minus 2 quantity squared. You can get this by essentially just cutting the b term in half or taking the square root of your c term. Either way it should work. And then you can simplify your coefficients. So we're factoring and simplify. Here is your vertex form of your equation. It's called the vertex form because now you can identify the vertex. It's your h and your k term. Now your h is always subtracted, so if it looks like it's -2, it's actually going to be +2. And your k term is just as it looks, so -5 turns out to be -5. You can also think of this as a transformation. Of the parent function x squared, shift it to the right 2 and down 5, so that's where we get the vertex 2, 5. If I wanted to do a quick sketch of a graph, which is where this might be very useful if you didn't have a calculator, I could quickly sketch wherever 2, -5 was. And now that I know my a value is positive and opens upward, I could quickly sketch it upward. And this is going to be what my graph looks like. In calculus, a lot of times we'll need to produce a quick sketch when we get to our volume problems or area problems. And without a calculator, some students struggle with this. So it's really important that you can produce a graph quickly using parent functions or any other methods, such as finding the vertex like here. And that's it for these notes.